So we're given the integral from pi over 4 to pi over 2 of the natural logarithm of tan of x over 2 divided by the sine of x with some disrespect to x. So this problem is really elegant because you can actually solve it by making 3 distinct substitutions. So the first thing I'm going to do is I'm actually going to make a substitution, one of 3. So first, let's let u equal to x over 2, which means that 2u is equal to x. Now we have that 2u du equals dx. Now we get 2 times the integral. So this doesn't look like we did anything because, as you can see, our angles still aren't the same. We have sine of twice u, but our tangent is just of u. So this doesn't look good until you realize that we actually have a formula for sine of 2u. It's the double angle theorem. So we know, as a fact, that sine of 2u is actually equal to 2 sine of u cosine of u. And we can use this fact right here to rewrite our integral. So now our angles are the same, and as an added bonus, we can actually cancel these 2's. So now we have same angles, but the only problem is, if we want to do a substitution, we need to have a secant squared u, because that will act as our du, because the derivative of tangent is secant squared. But we don't have that, but we can actually produce that by doing a little trick here. We can multiply the top and the bottom by cosine of u. And this is the same as multiplying by 1, so everything's fine. And this transforms our integral. And the way this works is, secant is the reciprocal of cosine, and since we have 2 cosines in the denominator, we actually have cosine squared. So the reciprocal of that is going to be secant squared. So now we can actually go ahead and make another substitution. We can go ahead and let w equal to tangent of u. We have dw is equal to the secant squared of u. And you'll notice right here we have the cosine of u over the sine of u. That's the same thing as 1 over tangent of u, so we actually get 1 divided by w dw. And this is perfect because it sets us up for one more substitution. We can go ahead and let v be equal to natural log of w, which will mean that dv is equal to 1 over w dw. And this is a very simple antiderivative to compute. We have the integral of v dv. That is simply going to be equal to v squared divided by 2. And this is going to be from x equals pi over 4 to x equals pi over 2. But you'll notice this is in terms of v right now. So let's go ahead and sub back in what v is equal to. V is equal to the natural log of w. So we have the natural log of w squared over 2 from x equals pi over 4 to x equals pi over 2. And this is going to be equal to, well, w, you can see it here is equal to tan u. So we have the natural log of the tangent of u squared divided by 2. And this is going to be from x equals pi over 4 to x equals pi over 2. And now we can actually plug in what u is equal to. U is going to be equal to x over 2. So this is the same thing as the natural log of tangent of x over 2 squared divided by 2 from x. And now that we have x in here, we can just write from pi over 4 to pi over 2. Now we can go ahead and apply the fundamental theorem of calculus. This is going to be equal to the natural log of the tangent of pi over 2 over 2 squared divided by 2 minus the natural log of tangent of pi over 4 over 2 squared divided by 2. Let's go ahead and look at this right here. Pi divided by 2 divided by 2 is going to be pi over 4. The tangent of pi over 4 is just going to be equal to 1. Then we're taking the natural log of 1, which is going to be 0. Then we're squaring 0 and dividing by 2. That's just 0. So our actual answer is just equal to negative this thing. So negative natural log of tangent of pi over 4, which is going to be pi over 8, divided by 2. And all of this is squared. Tangent of pi over 8 is equal to root 2 minus 1. So we have ln squared of square root 2 minus 1 over 2. And we can go ahead, oh yeah, this is negative. And we can go ahead and write this out really fancily as negative 1/2 times the square natural log of the root 2 minus 1. And this is our final answer.